So we've been talking about failure criterion. We've looked so far at the maximum shear stress criterion, which is also known as the Tresca criterion, or in some instances, the Guest criterion. We also looked at the distortion energy criteria. That's what we looked at last time. And so what we're going to do is answer an interesting question this time for a particular type of material that's out there that what we've done so far, we don't necessarily have something to deal with it with the two criteria that we've looked at so far. That question is this one that you see up here on the board. It's what do we do if we have a material for which the strength properties, the yielding strength properties, are different in compression than in tension. So, I mean, there's sort of some stuff built into this. You've learned in earlier strength of materials classes that our assumption for most ductile materials is that the strength values are going to be the same in compression as they are in tension. And that is true for many materials. So, generally most steels, most aluminum, most materials really do behave that way. But there are some materials that don't. Some materials have different properties in compression than they do in tension. What I want to do first here is explain one of the mechanisms that causes these sort of asymmetric strength properties, different properties in tension versus compression. And I'm going to do it in the context first of this type of material. It's called ductile iron. Ductile iron it's not a steel. All right, it is like a cast iron. Usually the parts that are made this way are made in a casting process. And the iron in the casting process generally ends up with graphite in the middle of the material. So the thing is, graphite doesn't have near the strength that the iron itself has. And what you have is, they call it a matrix. It's basically, think of like a Swiss cheese of iron that goes around a bunch of inclusions that are in the material. All right, so it's basically like these little bits of graphite are all mixed in with the material. The iron is the most strong part, and then it has this other stuff that's mixed in with it. What you see there with the cast iron there in the figure that's on the right, that is how some irons, based on how they're processed, that's how some irons end up with that graphite mixed in, and it's kind of in a flaky sort of a way. That makes the iron significantly less strong, especially in tension. Okay? The reason why is that it tends to be like broad areas of material where you do not have connection iron to iron. It's like a big wafer of graphite through the middle of it. The graphite doesn't really stick to the iron, and so it makes it have a lot less strength. And one of the things that they do to make ductile iron, and makes it have higher strength values generally, is they process it so that it makes those little inclusions of graphite, instead of being flakes, they become what they call nodules. They're kind of like little balls that are all suspended in that matrix. And by making them more nodular, as in being more like balls rather than like flakes, it makes it to where there's more connection iron to iron, and it makes the material a little bit stronger. And by doing that, it generally can start to achieve a level of ductility. So generally, one of the things that we assume is that we will call a material ductile if it can deform, if it can plastically deform more than about 5%. We will call it a ductile material. If it's less than about 5%, we will call it a brittle material. And by turning these flakes of graphite into these balls, it makes it to where you can have a ductile material rather than a brittle material. So that's kind of an interesting thing. Let me kind of describe, and hopefully it helped it make a little bit more sense. Why is it that it impacts your tensile properties more than the compressive properties when you have things that are included? So let's actually think about a piece of material. You can think of it as being iron with a piece of graphite in the middle of it. Let's say this is one of those little balls of graphite that's in the middle of this sea of iron. And then we imagine loading it. If you load it in tension, All right, what happens is there is no connection really between the graphite and the iron, and so one of the things that can happen is the iron can sort of pull away from the graphite. Right? It actually won't really connect, so it can sort of pull away, and it won't really hold any load. The graphite won't really add anything to how much load is being held in that piece of material or in that little volume of material. Well, what happens then if you switch this around and do compression instead? Yeah, so what would happen there is that it would actually make contact with the graphite, and even though the graphite might not be as strong a material as the iron, it would still make contact, and it would actually still contribute to the strength of the part. You can kind of imagine here, we're familiar with this. When we move things, we always have to do it with compression, right? Our hands can't apply a tensile stress to a surface, right? At least most of our hands. Sometimes I think my kids' hands can apply tensile because they're often quite sticky. But most of the time we don't expect that we're going to be able to apply much of a tensile force to a surface, but we expect that we can apply a compressive force to a surface with our hands. And it works very similarly for these things. It's, the iron can put a compressive force on the graphite, and the graphite can actually help to support some of that load. And this is, I'm using the example here of ductile iron, but this is really true for any material where you have some sort of a matrix of material that's kind of primarily responsible for things like strength or tension or those types of things, where you have another type of material that's included in it. And you can end up having these asymmetric properties in tension versus compression when you have that type of material. So this is kind of our justification as to why do materials like this exist, where you have a different yielding strength in tension versus compression. All right, so what we're going to do here is we are going to look at a way to deal with this case. All right, the basic idea that we're going to use, or we're going to start from, is the maximum shear stress theory, but we're going to try to adapt the maximum shear stress theory in order to allow us to have these asymmetrical properties. Okay, so the basic concept is still the same as before. It's that whenever you have your maximum shear stress in the material reaches the shearing stress that would cause the tensile specimen type of thing to fail, that's when you expect it will fail. Same concept, but now we have two different sizes of Mohr circle for a tensile specimen versus a compressive specimen. Okay, and that's what these two circles represent that I have on this chart right now. So imagine here, for a tensile specimen, you have one component of stress, right? One stress is applied. It is one of your principal stresses, and then the other two principal stresses are zero, right? And you load it to the point where it begins to yield. All right, so let's say that you've done that. You load it right up to the point of yield, and that is this point right here. So we'll call that value S sub y. And actually, we need a little bit more notation than this because we're going to have two different yielding strength values on this problem, right? So why don't we call it S sub y t? Because that's our strength, our yielding strength in tension. Okay? We can also do tensile testing, not tensile testing, but material testing, such that we apply the force in a compressive orientation. And you can do the same thing and load it to the point where it will yield. And so that would be this point back here, S sub y c. Okay? Now what we need to do on this is we need to use this sort of idea to come up with what is the transition from one of these strengths to the other strength. And so what you see there is I put this tangent line on these two circles that goes down. And basically what we have here is that if you imagine some other state of stress that's in between a pure tension and a pure compression, all right, some other state of stress, we would predict that it would fail whenever that state of stress got to where the circle, the Mohr circle that was created, went up and was tangent to this line as well. So it's safe up to that line, but if you go past that line with a state of stress represented by Mohr's circle, then that would be a failure. Does that make sense? Okay. So what I'm going to do here then is draw a state that is like that. Okay, here's a state of stress. Something like this. That is an arbitrary state of stress that's in between pure tension and pure compression. Okay. This state of stress doesn't have to just be principal stresses. It can be any state of stress, any state of plane stress with shearing on it or whatever. And from that, we can come up with what the principal stresses really are. So that circle represents a state of stress. All right. And so what we want to do is, for this state of stress, we need to analyze the geometry that we have here so that we come up with an equation that allows us to relate the principal stresses for this arbitrary state of stress. Let me go ahead and mark those on here. The principal stresses are going to be basically here and here, right? So I'm gonna mark those up top and just indicate that the coordinates of where these principal stresses happen are at these two locations. Okay, I'm going to call this one sigma A, and this one here I'm going to call sigma B. Okay, halfway in between sigma A and sigma B is the center of the circle. Right, so I'm going to put that on here as well. Say here's the center of my circle. And we can also do some interesting things here where we identify radial lines for each of these Mohr circles that I have here and show those radial lines extending up to that tangent line that goes relative to those circles. All right, so let me do that. So for this circle right here, there would be a line that extends up like this. I'll do it in a different color here for this one. There's a line that extends up like this for that circle. And there's another line that extends up for the tensile case up to that other line. Okay. And one of the things that I'm going to show you here is that we actually know quite a bit about the geometry that I have just drawn. All right, so I'm going to start labeling some things that if you disagree with any of them, let me know, but I'm going to start labeling some things and hopefully they make sense. Okay, so first of all, we know where this location is, right? This location right here is at S sub yt over 2, right? This light right here, S sub yt over 2. Okay, similarly, over here, we have that this is S sub yc. Okay. I'm going to do, instead of doing it exactly this way, I'm going to kind of describe the center point of the green circle slightly differently. I'm going to describe it more as a coordinate rather than as a dimension. All right, so if I'm going to describe that coordinate right there, what would I do? So I'll kind of mark this spot right here. What would that coordinate be? Okay, if you know sigma A and sigma B, what is that one in terms of sigma A and sigma B? Okay, it's really just the average, right? I've got those two coordinates, sigma A and sigma B. I'm halfway in between, so relative to the number line, it's really just the average of those two values. Okay, so that would be sigma A plus sigma B over 2, expressed as a coordinate of where that one is located. Okay? Let me put some other things on here as well. What is the magnitude of this radius right here? Right, it's SYT over 2. What about this radius over here? SYC over 2. This figure is going to get pretty messy, all right? I think I can get it all on there and have it still make some sense, but there's a lot of stuff I want to mark on here. All right, what about the radius of the green circle? Okay. Yeah, the radius is just half of the diameter. The diameter is the difference between sigma A and sigma B divided by, or the diameter is sigma A minus sigma B. To get the radius, you divide by 2, right? So sigma A minus sigma B over 2 is the length of that radius right there. Why am I doing all this? All right, it's a good question. What we're saying is that where we've put this green circle, it is right at the threshold of failure, right? So it is essentially a general case. It's some circle in between a pure tension and pure compression, and I've set it up such that it's right at the threshold of failure. Okay? So that means that I can relate my principal stresses, sigma A and sigma B, to my strengths, S sub yt and S sub yc, with the geometry of what I have written down right here. Okay? So what do we need to do? Well, there's a bunch of ways to do this. This is my favorite way of looking at it. Again, this is not necessarily the only way to look at it. But what I like to do is draw a line parallel to the green line starting at this point right here. Okay. And by drawing that line, it sets up a little triangle. All right, let me actually complete out that triangle that I want to look at. That's the triangle. That triangle has some properties. One of the properties it has is that it is a right triangle. Okay. Furthermore, this other triangle here is a right triangle. Those are actually similar triangles. Okay? Since they are similar triangles, I can set up proportions between those two triangles for various sides. Like, corresponding sides have to be proportional in length. Right? So that's the principle that I'm going to use here. Tell you what, I'll take that triangle and I'll draw it bigger. Okay, and we'll try to identify lengths of a couple of the sides. Let's start with this one right here. Okay, this side right here is how long? Okay, close. It's S sub yc over 2 minus S sub yt over 2 because we had this little length right here that we subtracted off by having these parallel lines. Right? So that would be S sub yc over 2 minus S sub yt over 2. Okay? What about this little piece right here? Okay, using the same type of rationale that we used at first. And I'll tell you what, down along the bottom here, I'll use two different colors. I'll say this portion of the triangle right here in the red, how long is that? This is one of the trickier ones. What's that? Okay. Keep in mind that I know the coordinate of this point right here. Right? I know the coordinate of that point. Is that coordinate where I have it drawn right here, is it going to be a positive value or negative? Okay, it'll be a negative value. If it's a negative value, then how do I take it along with SYT over 2 that I have here to figure out what that length is? Okay, it's kind of adding together, but it's a negative number, right? The more negative it is, the more that length grows. So I don't actually add, I need to subtract, right? That's kind of counterintuitive. Another way of thinking about it that might help you understand that is what if I had chosen, since I just chose a random location for that circle, what if I had chosen the location over here? Like right here. All right? If I had chosen a location right there, then it would make sense to take S sub yt over 2 minus sigma a plus sigma b over 2 in order to figure out what this little length was right there. That make sense? So anyway, I wanted that to make sense. S sub yt over 2 minus the coordinate at that location is sigma a plus sigma b over 2. All right. And then I guess I'll use blue down here. For that length, what do I have? That one's pretty easy. That'll be S sub yt over 2 plus S sub yc over 2. Yeah, this whole bottom length. Okay, so let me show you here that if I turn all of that triangle blue and I turn all this other triangle red, the red and the blue triangles are similar. Okay, because they're similar, I can take corresponding sides and set up proportions. So that's my next thing that I'm going to do is take corresponding sides, set up those proportions. All right? So let me start with, I guess, let's see, I guess I'm trying to think of what the most clean way is to do this. All right, let's set it up like this. Let's take S sub yc minus S sub yt over 2. Okay, so basically I'm working with this right here. And I look at how that corresponds with sigma a minus sigma b over 2 minus S sub yt over 2. So let me make sure we know where those came from. Yellow goes to yellow, blue here goes to blue. This is going to be equal to these other two sides that also relate to one another. So, and we need to make sure we set them up in the same direction, right? Up here I'll have S sub yt over 2 plus S sub yc over 2. So that's this right here going there. And lastly, I have this side right here that will correspond with this denominator here. You don't like that purple, huh? Yes, I can do a different color. Let me see what I can come up with. How about, I'll try this one. No, that's even worse. Let's see. How about light blue? Is that better? Or I could just leave it unhighlighted and let it be a process of elimination. All right, sigma A plus sigma B over 2. All right. I could work a bunch of algebra right now if I wanted to. And even if I wanted to, which, every now and then doing a little algebra is not too bad. But I'm going to skip it. After many dot, channeling Dr. Lee. What this gives us is an expression that says sigma A over S sub yt minus sigma B over S sub yc is equal to 1. Okay? This is for the situation where the green circle goes up and literally goes tangent to this line that describes failure. All right? If you want to include something else in there that is a factor of safety, something that basically allows you to, a parameter that helps you move it off of that, impending failure. How do you think you would do that? Okay. It's kind of how it is. You basically imagine you wouldn't want this circle to get quite that large, right? So one way you could do that is by just moving the line down, right? And that would just sort of decrease the size that you could have for the green circle, right? And so if you think about this, what that would do is it would, relative to A and B, if you want those A and B values to predict lower, you would want this value of 1 to be lower, right? So that's what you do. You basically divide this. Instead of having 1, you have 1 over your factor of safety. You could also think about that in terms of strengths, right? If you wanted to make your part stronger, then you could use stronger materials. That would decrease the values that are in the denominator here, okay? And you'd achieve a similar idea with that factor of safety. All right, quick comment on this before we move ahead and do a problem. The comment I want to make on it is that this negative sign that we have right here, this is confusing for some folks, and so I figured I'd talk about why do we have this negative sign right here. The reason we have the negative sign is that generally data that is in tables about strength of materials is always stated as positive numbers, even if it's for a compressive stress, right? So the SYT and the SYC are always going to be given as positive numbers, right? What about A and B? Okay. Well, what are the limits on what A and B are allowed to be for this derivation that I just did? Okay. My assumptions here begin to break down if I move outside of the circles where I have a tensile specimen and a compressive specimen. Okay. And here's why. If I move to a circle, let's say, and I'll choose a different color here. Let's say I go to a circle that's way out here. Could I have a state of stress, for instance, that was out here? Is that a safe state of stress? Okay? Yeah, so it's tempting to think that it might be safe because it's sitting there inside of that line, right? But it's not safe because one state of stress that I have implied, once I say that this is my state of in-plane stress, there's an out-of-plane stress that's implied that does this. Back to 0. And does that stay inside of my envelope? It does not, okay? And so what we have here is that our limits are actually chopped off once we have both of our principal stresses positive or both of our principal stresses negative. We don't continue to use this expression, okay? This is if sigma A is greater than 0 and sigma B is less than 0. Okay, what happens if we have both of them greater than 0, for instance? Let's always assume here that sigma A is the largest one. So let's say they're both greater than 0 and sigma A is bigger than sigma B. Where do we actually expect that it will fail? Okay, it'll probably be controlled by just the one. So if you actually imagine here a state of stress, I'll do even another color. Let's say I do another state of stress. And I put it right here. Here's my in-plane stress. Do I expect that that will fail my material? Why not? Yeah, because that state of stress, that state of in-plane stresses implies an overall shearing stress that does this. Right? That would be my Mohr three-circle diagram for this problem. Okay, so my maximum shearing stress is right there at the threshold. So my point with this is that if you end up with a state of stress where both of your in-plane principal stresses are positive, whichever one is the highest one, furthest to the positive on the number line, is going to be the one that controls whether it will fail. And it will do so at the stress threshold that corresponds with the tensile specimen, right? And so what we say here is that, if we look at our sigma A over S sub yt equals 1 over n, okay? This is what it is if sigma A greater than sigma B greater than or equal to 0. Okay. Do you think we could do something similar on the compressive side? Yeah, so I'll do one of those now. So let's say that we, over on the compressive side, okay, let's say I had a state of stress that was right here. That would imply there would be a maximum shearing stress here, and that would be right at the threshold of failure. Okay? So basically what we're saying there is that we would have sigma B, and I would really actually say negative sigma B because sigma B is going to be a negative value, but S sub yt or S sub yc is going to be a positive value, right? Is equal to 1 over n, and this is what we have if, okay, I'll say sigma B is less than sigma A, less than or equal to 0. Aha. Thank you. Meant to draw those that way. That's another one of those Easter egg mistakes for you to find. part of the plan. All right. So that is our, that is what we have as far as our failure criteria is concerned. Let me do something else real quick. Let's figure out, I have a problem I'm going to work in just a minute. Let's figure out what this would look like on our plane that we've been plotting these things on, where we have sigma A and sigma B. Okay? So let's say we have sigma A, sigma B. Where would my thresholds be? In the positive direction. All right. I would have S sub yt and S sub yt. And if either of those, if your stress level got up to either of those, whichever one was greater would be the one that would control failure. Right? And so you end up with a little box up there like that. Okay, you typically expect that your compressive stresses will be larger if you have asymmetrical strength parameters for a piece of material. And so, that might look bigger. This part back here might look a little bit bigger. And these two things would be negative S sub yc and negative S sub yc. And in between, we have these slanted lines. And that would be the failure locus for this is called the Ductile Coulomb Mohr criterion. And keep in mind, sigma A and sigma B, these are in-plane principal stresses. All right? Should we work a problem? All right, what we have here, we have a piece of machinery that is being driven by a belt. And we might actually assume this is a flat belt. Flat belts don't transmit any torque unless you have some amount of pretension in the flat belt. And then what they do to transmit torque is that the two sides of the flat belt, they're both carrying tension, but they carry different amounts of tension as it drives the piece of machinery. Right? And that's what actually introduces torque into the piece of machinery. All right? So what I've shown there is that I've got these two forces representing the belt that would be pulling on the two sides of the pulley. All right? We will assume here that it is either stationary or turning at a constant speed. Okay, at this point, we don't necessarily care which of those. All we care about is we don't want it to be accelerating because that will complicate it, right? So we'll assume here it's turning at a constant rate. All right, and what we want to do is to determine what the factor of safety is against yielding this shaft using this Ductile Coulomb Mohr criterion. The shaft is made out of a grade 60-40-18 ductile cast iron. Okay. The way the geometry works here is that the shaft has a 20 millimeter diameter. The pulley has a 20 centimeter diameter. And the amount of extension that we have away from the piece of machinery is 15 centimeters. So imagine that pulley there is hanging on a 15 centimeter long cantilever hanging out of the piece of machinery. Okay? Where do we start? Okay. I heard one person say free body diagram. I heard someone else say find some normal stresses. You can do a free body diagram if you'd like. I generally don't discourage that. That's a lot of times a good thing to do. It might be something you don't need to do on this one because it's fairly simple, right? Let's actually try to identify where is the critical point likely to be for this setup. Yeah, like a patch of material basically right there, right at the little, where the shaft starts to enter the machine. That's where we're going to have our maximum flexural stress. Our shearing stress due to torsion is going to be constant around the entire perimeter of it. We do expect that the critical location is going to be on the surface of the shaft, not buried somewhere inside of it. It's going to be on the surface of the shaft because that's where our stresses are the maximum. Okay? And so we're looking at that little patch of material right there. How do I figure out what the what the flexural stress is, for instance, on that patch? Let me do this. This is probably going to be a helpful thing. I can take these two forces that I have applied out on the edges of this pulley and imagine relocating them to the center of the shaft. And that's okay for me to do as long as I also evaluate the torques that were also generated by those two forces. Okay? So if I do that, imagine here I'm going to take my 90 and my 450 and put them right here. Okay? And what would that magnitude of force be? 540? Okay, so now we've done away with this one and this one. But what else do I need to do to make that valid? Okay. A couple of ways you can think about this. Each of those forces creates a moment, but they're in opposite directions. The amount of moment we're going to have is going to be 90 newtons times 10 centimeters one direction and 450 newtons times 10 centimeters the other direction, right? So what I can say there is that I'm going to end up with a net torque in this direction, and that torque is going to be equal to 10 centimeters times 450 newtons minus 90 newtons. Okay, that's 3,600 Newton centimeters. All right, now what? Okay, we can do the flexural stress. I'm good with that, so we'll do that over here. MC over I. Okay. What's that bending moment going to be at my critical location? Okay, 540 newtons times 15 centimeters. Yeah, that's a good idea. Let's change it to millimeters. You guys learn quick. Times what? Okay, yeah, 20 millimeters divided by 2, which is 10 millimeters. All this divided by pi over what? pi over 64 times the diameter of the shaft to the fourth. So I punch all this stuff in. And I'll make the comment again here. If you ever end up with units of newtons per square millimeter, that will translate into megapascals. Right? Remember, millimeters times 10 to the negative 3. That squared is times 10 to the negative 6. Move to the numerator. It's times 10 to the positive 6, which is a mega, right? A million. All right? So, what do I have there? 103.13 megapascals. Say what? It is positive up there at the top of the shaft, yes. Which is that is more likely to be your worst case scenario, right? In many cases it wouldn't matter, but for this material it matters, right? Your material is weaker in tension. And so you want to look at the state of stress that's going to be worse, and the state of stress that's worse is one where you have a more positive tension rather than a more positive compression. All right, so that's kind of a tricky thing that we did sort of without analysis. It's worthwhile mentioning.
How do you find out, like, you looked at the numbers in the tables to see that material is...
Yeah. Yeah, okay, so you're jumping ahead one step. Let me go ahead and get my stress due to torsion, my shearing stress due to torsion, and then we'll get to that step in just a second. Is how do we figure out what the material properties are? What I'm given is this type of ductile cast iron, and so I'm going to need to do something to figure out what are the strength properties of that. And so that'll be the next step. All right, so torsional stress. TC over J. Okay. What we'll have there is the torque being 3,600 Newton centimeters. What would that be in Newton millimeters? 36,000 Newton millimeters. Okay. C is the same as it was before. It's the radius of the shaft, which is 10 millimeters. J is the polar second moment of area for the shaft, pi over 32 times the diameter of the shaft to the fourth. So I'll punch all of those items in. 36,000 times 10 times 32 divided by pi times 20 to the fourth. Let me make sure I didn't make any errors there. Seems a little bit low, but it could be correct. All right. 22.91 or 92. Let me check. So there are our two stress components, flexural stress and torsional stress. One good justification as to why that may have come out a little bit low is we are pulling with tension on both sides of this pulley. So that can lead to a large amount of flexural stress or bending moment, more so than the torque, right? Anyway, I'm reasonably confident that I didn't make any errors there. All right, well now what? Yeah, we need to figure out what our principal stresses are, our in-plane principal stresses. Okay, this is where Mohr's circle works really nicely. And I won't even draw it this time because it's the same exact situation that we had with our last problem. When we look at this problem, one of our normal stresses on that patch is going to be 0, right? If you actually go back up and look at this patch, the only stress component that we are looking at in the normal orientation goes that way. We do not have any stress that goes in sort of the hoop direction around the outside, the perimeter of the shaft, okay? And then we will have a shear. So we have one component of normal stress and one shear. So that means that we'll put that component of normal stress right here, 103.13 MPa over 2, plus and minus the square root of 103.13 MPa over 2 squared, plus 22.92 MPa squared. All right? And we'll punch that in as well. Let's see here. Let's do it this way. 103.13 over 2 plus the square root of 103.13 over 2 squared plus 22.92 squared. And that gives me 107.99 And what's the other component? What do I have to change here? All right, and that gives me a negative 4.86. megapascals. All right, so then what? Yeah, we need to know what our strength values are. And one of the things that's a little bit annoying about this textbook is they don't give you any sample data for materials that are both ductile and have asymmetrical strength properties in tension and compression. So I had to go elsewhere. And so I'll pull up a website here. This is just on Google Books. I found a reference book. It is ASM Specialty Handbook for Cast Irons. And in there they have a couple of tables. And one of the ones that you'll see here, this is our material, 60-40-18. And basically this is saying these are some expected values that you might have for these grades of ductile cast iron. Okay, what you'll see here is that we're expecting a yield strength of 329 MPa in a tension. Okay, and we're expecting 359 megapascals in compression. All right, and I've actually made this table and one other table available for you on Moodle, so that if, in case we have some problems where you need to use this information, you'll be able to look that stuff up. All right, so those are our strength values. S sub yt was 329 megapascals. S sub yc was 359 megapascals. All right. Our principal stresses, one of them is positive and one of them is negative. And so we are in the segment of the line that is sloped right here. We're in this, this portion right here. Okay, so we will use that as our equation to find our factor of safety. Okay, I'll get those strength values in there. All right, 107.99 MPa over S sub yt, which is 329 MPa, minus a minus 4.86 MPa over 359 MPa. This is equal to 1 over n. Okay, and therefore n is equal to, I don't have this one done already, so I'll calculate it real quick. All right, 107.99 over 329. The negative and the negative make up a positive. 4.86 over 359. This is going to be equal to 1 over a variable. I'll tell it to solve, and that gives me a factor of safety of 2.926. Well, you'd have to do 1 over, 1 over all of this equal n, right? All right, so there is my factor of safety using the Ductile Coulomb Mohr criteria. All right, let's do one other thing. Let's plot the load line on the set of axes for the failure criterion. I'll do it by hand in this particular one. All right. Trying to think of how big to make my squares here. I think I'm going to make each square worth I think each square is going to be worth 50 megapascals. That might end up making it a little bit small, but I don't want to get too far off of there either. Okay, so 50 megapascals per square. I'll tell you what, we could probably do 25. Sorry. We'll do 25 per square. Will that work? All right. So we need to plot 329 megapascals on here. So this would be 100, 200, 300, and so we'd be out about at that location. About like that. Okay. 329 megapascals. And this is on sigma A, sigma B axes. And that would also be 329 megapascals over there as well. All right, down here I'll have 359. So let's see, 100, 200, 350 will be down about there. Okay, so we've drawn our failure locus here. This is 359, or negative 359 megapascals at this point. And this right here is negative 359 megapascals. And what about plotting our load line? Okay, it's not actually very far down off of my just straight rightward axis, right? But it goes over by 107.99. Okay, so I'll plot that maybe over here, you know, roughly here and roughly here. And that would be at 107.99 megapascals and negative 4.86. Okay, and just to kind of reemphasize the point of what the load line means, if I was to extend that load line further along the same direction and look at how long that line would be to get all the way out to the failure locus, the ratio of that longer line over the shorter line, the length of the shorter line, that ratio would be my factor of safety. Okay, does that look like it's about right, that that ratio would be 2.926 or so? I'm sorry, what? Yeah, about a third or so of the line looks like it's covered. So it looks like our failure locus plot here and the load line agree with what we calculated algebraically. Yes, sir?
So it's the distance from the origin to that edge of the locus line, all divided by that short line.
Yeah, I'll go ahead and draw it on here. So I'll do it in two colors. If I had a line that extended from the origin all the way to there, and I take the length of that line and divide by the length of this green line, the ratio of those two lengths is my factor of safety. All right? Questions before we go? Wonderful. I will see you guys on Friday.